We'll now do this second lecture on exploring random maps.
Okay, thank you. So let me start with a brief reminder of where we were last time. So we are considering again this model of Boltzmann planar maps defined from a weight sequence Q. So with this weight sequence Q, you associate a sigma finite, say, measure on the set of bipartite maps by this formula, and then you consider the partition functions that are obtained by taking the total mass, say, of the family of all bipartite routine maps with a fixed root face degree, say equal to 2L. And there was also a pointed version that was obtained by not only summing over all bipartite maps, but also having the number of vertices as a prefactor. And then the proposition that I stated last time, and that I want to start with proving today, is this admissibility criterion for Q, namely a condition under which these partition functions are well-defined finite numbers. Okay, and this criterion was stated very simply in terms of this generating function GQ of X for these modified weights QK. And it says that Q is admissible, so in maybe the slightly stronger sense that W dot Q is finite, but as I said last time, it's actually equivalent to the fact that W, say W1 of Q is finite, if and only if GQ of X equals X admits a solution. And in this case, the smallest such solution is actually the generating function of slices, so which is also given by 1 plus W1 dot Q over 2. And I spent some time last time explaining what a slice is and how it's related to, in fact, a model of both rooted and pointed map. Okay, so I won't recall the definition here. And I'll start with something that I only briefly sketched last time, which is that you have actually a nice bijective decomposition, bijective description of these slices in terms of certain trees. So let me start with explaining what these trees are. Last time what I tried to sketch was how you constructed the first generation of the tree by sort of exploring the first face of the map lying on the other side of the root. But what you do when you completely unfold a slice with this procedure is this kind of object. So these are trees with two types of vertices. So you have white vertices that actually correspond to the vertices of the map, and you have black vertices that correspond to the dual vertices, namely the vertices lying in the faces. Okay. So this is written here. So black vertices in the tree correspond to faces of M, and actually the degree of the faces, or the half degrees, correspond exactly to the degrees of these black vertices. Okay, so the degree of this vertex corresponds to the degree of the face of the corresponding face divided by 2. And the white vertices, so again, they correspond exactly to the vertices of the slice here, except the distinguished vertex V star. And you also have a label assigned to all of these vertices, and this label, in fact, corresponds to the distance of the corresponding vertex to the vertex V star. And in fact, in order to make that slightly simpler, you actually subtract the distance from the root. So the root being the vertex sitting at the bottom of the slice, from the root to V star. And this simplifies things because it makes the resulting tree to have always a label 0 at the root. Okay. Now this completely describes the kind of trees that you obtained. So these are again trees with these two types of vertices. These two types alternate from one generation to the other. So white vertices give birth only to these black vertices and vice versa. And the only thing that remains to be explained is what is the rule for these labels. And this is illustrated on this particular example. The rule is that when you go around a black vertex clockwise, then the difference of labels has to be an integer bigger than or equal to -1. So for instance, starting from this one, you can indeed subtract 1. Okay, so this is what we do here. From 1 we go to 0. You can again subtract 1. You cannot subtract more than 1. But on the other hand, you can jump by any non-negative number. Here in this particular case, you jump from -1 to 1 directly. Okay. Of course, you couldn't go from -1 to 2 because otherwise you couldn't go back to -1 in just 2 steps. So this actually limits the number of possible labelings around the black vertex. And it turns out that this number of possible labelings is exactly equal to this combinatorial factor. So this is actually, this corresponds to the number of possible labelings around black vertex of degree k. Okay, so this at least explains where this comes from. And again, this is a bijection. It's possible to go from trees to slices, and I'm not going to describe for you the inverse bijection. Okay, so I'm going to prove the proposition now, and in order to do that, I'm going to use a further simplification because, okay, these labeled mobiles are very nice objects, but it turns out that there is a very nice transformation that allows you to sort of get rid of this annoying difference between the odd and even generations and the different types of vertices. And this correspondence is a nice correspondence due to Johnson and Stephenson. And it goes in the following way. So it's a transformation that's going to assign with one of these alternating types, two-type trees, a tree with only, you know, in the end it will be a one-type tree, but for now we are still going to keep the types, except that all the black vertices will now be internal vertices, and all the white vertices will be leaves of the tree. And how do you do that? Well, first of all, you start from the first available black corner in the tree, and then the rule is that you are going to try to link the black corners by order of priority, either to say its grandchild, or if it has no grandchildren, to its child, okay, or if it has no child, to its younger brother, or if it has no brother, to its parent. Okay, so you have this kind of priority rule. So let's try to see how it goes. So for instance, in this particular instance, this first corner has indeed a black grandchild. So we link it to this grandchild. Now we try to start from this corner, and it has no grandchildren. So what we do is we just link it to its child. And then we move on to the next available corner here. This has no grandchildren, so we again link it to its child. Then we are at this corner, and this corner has, you know, no more grandchildren or children, but it has a younger sibling. So we link it to here. And then this one has, you know, no descendants, so we link it to its parent. And we continue in this way. So you obtain something like this, maybe. And this gives you a transformation, again, from this set of trees to a set of trees in which all the black vertices become internal vertices. And what you can do also is you can, in fact, assign a label to the internal vertices by saying that every black vertex inherits the label of its parent. So for instance, this one is going to inherit the label 0, this one is going to inherit the label 1, and so on and so forth. So 2 and 1. Okay. So this is what I've written here on this side of the blackboard. And this is again an operation that you can invert. That you think about the construction from this side to this side. It's actually a nice construction. And if you think a little bit about it, then you will see that the resulting tree, so it's a label tree, the rules for the labels will be the exact same as above, except that what you do is you go from a parent to its children, and again the delta of labels has to be greater than or equal to -1, with the extra constraint that the last label must actually be equal. Okay. If you think about it, it's not very difficult to see that the number, the degree of the black vertices on this side of the blackboard correspond actually to the number of children. Okay, meaning that you somehow you have one extra step on this. Okay, so, yeah. The number of yellow intervals, if you like, that are sitting here is in fact one more than the number of intervals that were sitting there. Okay, so but you resolve this by saying that the two labels here are actually the same. Okay, but other than that, you have the same rule. So why is this useful? So let us now prove the proposition. So let us assume, well, for now, let's not assume even that that Q is admissible. Let's just use this bijection with slices. Okay, so due to the Buttieri-Francesco-Gitter and Johnson-Stephenson bijections, so if we want to see what a slice is, well, a slice is either a trivial vertex corresponding to the situation where the two-type tree has only one white vertex. It actually the slice, in fact, with my convention corresponded to this trivial situation here, or a slice corresponds to okay, that was actually okay. This was actually in correspondence with the trivial tree here, or it has to be a non-trivial slice, which will correspond to a tree in which you have at least one internal vertex. Okay, and this internal vertex can have potentially any number of children. Okay, so you get a sum over the possible number of children, has to be greater than or equal to 1. Well, of first of all, the number of possible labelings of these children, and this is 2k minus 1. Okay, so this is the number of possible labelings. Of the root's children. And then what do you get? Well, each of these children is going to give rise to a tree of the same type as before, which in turn encodes a slice. So you just get the generating series, generating function of slices to the power k. Okay. And if you think about this, then and of course, this participates. If you have a vertex of degree k, this participates, of course, in a weight qk. In the definition of the weight of the corresponding map. Okay, it participates with a qk, and this is exactly gq of rq. Okay. So in particular, it tells you that even if q is not admissible, it will always satisfy this fixed point equation, but of course completely trivially if it's not admissible. And so if q is admissible, then okay, rq equals to gq of rq is finite. And conversely, so let's finish the proof. So conversely, assume that x equals pq of x is a solution, a finite solution, okay, is the smallest possible fixed point with x in with a finite and greater than 1. Okay. Again, it has to be greater than 1. So, in this case, what we are going to do is let us look at yeah. So let's write fix say a slice M, and with it we associate you know a label tree TL by the bijection that I described before, PDG and Johnson-Stephenson. Okay. And I want to write the weight of M. So this is the product over all faces of M of Q degree of F divided by 2. So these are actually the interior faces, okay? Degree of F divided by 2. And in terms of the tree, it's also the product over all V internal vertices of Q of C of V. So C of V is going to be the number of children of V in T. But in fact, okay, I can just bar the word internal because if a vertex is not internal, it has to be a leaf, so it has 0 children, and my convention was that Q0 is equal to 1. Okay, so I can just put that here. Okay. Now, if I want to sum over all possibilities, you know, over all maps, then, okay, let us consider okay. So consider all maps M giving rise to the same, to a given tree T, and of course possibly with different label. Okay. Then let's call that maybe the set M T. Then this gives me that WQ of MT is equal to the product over all vertices of T of QCV times the number of possible labelings. Okay, so I just get a Q tilde of CV. Okay. Okay, so now let's just divide this by X. And what I want to say now is that I can rewrite this product in the following way. I can write this over the product over all vertices of T of X to the number of children minus 1 times Q tilde of CV. Okay? That makes sense because if you take the product of all vertices, you get all the possible children of a vertex. So you get all vertices except the root vertex, which is the children of no one. And you get a minus 1 for every vertex. In the end, you just get this 1 over X. Okay? So let's call that mu Q of CV. And we just recognize, we can interpret this, of course, this quantity, you can interpret this as the distribution function, I mean the probability law of a Galton-Watson tree with the probability of string distribution given by this mu q of CV. Okay, and yeah, And now what you obtain is that, so consider there's actually something there's actually something missing here. Yeah, sorry, of course. So, and this is a probability distribution function precisely because x is a solution of the fixed point equation. Okay, so mu q k equal to x to the k minus 1 q tilde of k is a probability distribution function on z plus. So because of the fixed point equation, x equals gq of x, okay, and therefore this says so the right hand side is equal to the probability that t is equal to a particular given tree t, where t is a Galton-Watson tree with a swing distribution mu. Okay, and in particular, if you sum over all possible trees, well, you will get just the probability that a Galton-Watson tree with this swing distribution is finite, okay? And this will sum to 1 if and only if the tree is subcritical, okay? But then, since x is the smallest solution of gqx equals x, one must have that the derivative gq prime of x less than or equal to 1. Okay, so if I draw again the picture, you have something like this. You have a convex function and you take the smallest solution. So the derivative has to be less than 1. And this exactly says that mu q is subcritical. Critical or subcritical. And in particular, so if you sum over all possible trees, you get 1. And let me finish the proof here. So therefore, WQ of all slices divided by x is equal to 1, and WQ of slices is just RQ. Okay, and that finishes the proof. Any question about that? Okay, so yes.
The BG bidirection for slices, not for the maps.
Yes, so but it's the same. I mean, slices are the same as rooted and pointed maps, in which the root points to the distinguished vertex. Yeah, I mean it's the natural. It's really the natural object. Or, I mean, otherwise I would have to say rooted and pointed maps in which the root points to the distinguished vertex. No, but you are right. I mean, there is a slight ambiguity on whether I actually cut open the map along a geodesic corner. Okay, but combinatorially it's just the same.
Gregory?
Yes.
The proof of the proposition, in the first case, do you have to check that it's also the smallest solution, or it's follows?
It follows from the second part. Yeah, it follows from the second part. Okay. So what we learned from this proof is, of course, that there are branching processes that are hiding behind these random maps, and this is actually useful to consider scaling limit results. So maybe this was a part 1 proof of the proposition, and part 2 is first the scaling limit results. Okay. So the idea is that if you understand the behavior of the labels inside this kind of random trees in which the labels have been chosen uniformly at random among all possible all admissible labels, then by working going back the flow of bijections from the trees to the maps, you will understand the distances in the maps. Okay, so let's say Mn be a slice, say a random slice with distribution. So let's say PQ conditioned on having n edges. So where PQ is just WQ restricted on slices divided by RQ. And this is actually, if you want, the conditional law on slices. And let Tn Ln be the label tree associated with Mn via, well, these two bijections, Buttieri, Francesco, Gitter, and Janssen, Stephenson. Okay. So by what we've seen so far, it so happens that then Tn, so if you forget the labels, is a Galton-Watson tree with offspring distribution uq. So of course, sorry, I'm assuming of course here that q is admissible. So let q be an admissible sequence. Okay. So obtain here a Galton-Watson tree with offspring distribution mu-q, conditioned on having actually n plus 1 vertices. So it's something which is quite easy to see. The total number of vertices of the tree is going to be the number of leaves plus internal vertices. Okay, internal vertices correspond to faces, and leaves correspond to vertices. So you just get the sum of vertices plus faces, and by the Euler formula, this is the number of edges plus 2. And in fact, by counting the leaves, you in fact forget to consider the distinguished vertex, so you have one less. Okay, so that explains the fact that you have only n plus 1 vertices there. Okay, and conditionally given Tn, Ln is uniform among, let's say, the product over all vertices of Tn of the possible labelings, which are, if I'm right, twice the number of children minus 1, choose CV, so among all possible. Now, before stating the first theorem, let me give another definition. So we say that Q is critical if Q is admissible and moreover it's it's just barely so, in the sense that GQ and the identity are tangent at the unique solution. Okay, and if GQ prime of RQ is actually equal to 1. Okay, so which is of course equivalent to saying that mu Q is a critical distribution. Okay, here I should be maybe slightly more specific. So before I define this mu Q in terms of x, it should be clear here that x is equal to the solution. Okay, so I should here define mu Q as being really RQ to the k minus 1 times Q tilde of k. Okay? And now let me state the first theorem. So slightly informally stated. So assume Q is critical and that it has a finite second moment. Okay, so I'm going to assume that sum over k minus 1 mu Q of k, k greater than or equal to 0, is non-zero and finite. Okay, so this is a second moment assumption. Then there exist constants that I'm going to call little sigma and capital sigma that both depend on Q, such that, so if you consider the tree Tn and the labels, then, okay, so as is very well known, when you have a Galton-Watson tree with finite variance of ring distribution, then if you condition it to have a total population size n or n plus 1, then the typical height in the tree is going to be of order square root of n. Okay? And in fact, if you renormalize the distances, so let me sort of divide the edge length in Tn by square root of n times this little sigma, then this converges as n goes to infinity in distribution to an object which is called the continuum random tree, or the Brownian continuum random tree, so called Brownian CRT. Okay, so this is a very well-known fact due to Aldous. And so what sorry, what does it tell you? It tells you that the tree Tn again has a typical height of order square root of n. Okay? And if you look at the labels, if you go along the tree, then of course the label differences, they will, vary in a kind of complicated way and very dependent on the degrees of the vertices that it encounters. But the idea is that in such trees, the typical degrees remain very small. So in fact, the label differences, the label increments along the typical branches of the tree is going to look very much like, let's say, a simple random walk, or at least a random walk with a finite variance. So this tells you that if you want to look at the difference of labels between the root, say, and a typical point at height square root of n in the tree, then it should be at this label should be at a level which is of order square root of n. Okay, because of the central limit theorem, but applying for a sum of square root of n random variables. And indeed, if you renormalize ln by this capital sigma times n to the 1/4, then this converges to a process z, which you should understand as the Brownian motion on the CRT, or I should say maybe indexed by the CRT. So this is, if you want, one of the possible avatars of the Brownian snake. That was introduced by Le Gall. Okay. So again, this is a theorem which is stated in a very informal way, because I didn't really mention the topology of the convergence. And actually, this will be discussed by Cyril Marzouk in his talk tomorrow morning. You can make sense of it by taking contour processes of the trees and show that they converge to the corresponding contour processes of these two objects, which in this case is a pair formed by a Brownian excursion and a slightly more complicated object, which you can see as a Gaussian process on Z. And actually, this pair of processes has, in fact, a little bit to do with the mating of trees that Jason is discussing in his lectures, except that this is of a very different nature. I mean, you don't have a pair which is made of two Brownian components. One of them is indeed a Brownian excursion. The other one is something of a very different nature. Okay. So, any questions about this? So, for those of you who are not familiar with the Brownian CRT, you should really imagine that it's a large-scale limit of a uniformly chosen tree, and it's an object which is a random R tree, which you should picture as a gluing of an infinite collection of real segments, a countable infinite collection. But when you've glued all these segments together, forming a kind of random tree structure, you are not there yet, because you still have to get to do some completion operation to actually get the right object. My point here is that this object still has a kind of non-trivial fractal structure, and in particular the Hausdorff dimension of the set of leaves is equal to 2. So it's something a little bit complicated. And Brownian motion on the CRT, well, you should think of it as you fix a point in the tree, say A, then the label of this point A will be the same as that of a Brownian motion run for this time interval. Okay, and if you want to get the label of say another point B, then what you are going to do is you are going to run the same path of Brownian motion up to the branch point, and then continue by performing a completely independent path of Brownian motion. Okay. So it's not going to be extremely relevant, in fact, in the in the remaining part of my lecture, but I at least want to say that these are the kind of building blocks that you need in order to construct the objects that I will now discuss. And again, an important thing here is that the limit does not depend, in fact, on Q. This is something that is completely universal, if you like. It's universal in the same sense as Brownian motion is the universal limit of random walks with finite variance. Okay. Okay. And so this theorem has the following consequence. So a theorem. So again, let Q be a critical weight sequence. Again, with finite associated variance, so sum of k minus 1 mu q of k non-zero and finite. Then, if you look at the set of vertices of Mn, and you view it as a metric space by putting the graph distance on Mn, so this is the graph distance. And again, these distances, they more or less correspond to the labels here. So you should rescale this by this constant sigma times n to the 1/4. Then this converges as n goes to infinity to a limiting object, which I'm going to denote by ST, which is called the Brownian map, or the unit volume Brownian map. And this convergence holds in the so-called Gromov-Hausdorff topology. And Gromov-Hausdorff topology allows you to compare different compact metric spaces. Okay, so one way to think about this is that it is possible to construct both this object and the limiting object on the same probability space in such a way that these objects are isometrically embedded into some bigger space Z delta in such a way that the Hausdorff dimension between Mn and the limiting space S is small, vanishes as n goes to infinity. Okay, so the Hausdorff dimension. That's one way to understand this theorem. Okay, so this theorem is due so it's actually due to Le Gall. I had an independent proof of this result actually in the particular case of quadrangulations, and in this generality it's actually due to Marzouk. With assuming only the finite variance assumption, and he's going to tell us more about that. He has a more general result. Okay, so what does that tell us? This maybe not much at this stage if I don't tell you what the limit is. And it turns out that we know quite a bit about the limiting space. So the limiting space SD is a random compact geodesic metric space which is homeomorphic to the two-dimensional sphere. This is due to Le Gall and Paulin. And it has Hausdorff dimension 4. And of course, this was almost surely. And this is due to Le Gall. So you should really picture this limiting space as a kind of a random sphere, but with a very fractal behavior. It is a topological manifold. But the fractal dimension is equal to 4. Okay, and I'm not going to tell you much more about this space. You can construct this space as a measurable function of the pair that I've written here. But if you want to actually prove this theorem, you need much more. It's quite a bit of work. So here I was a little bit vague, in fact, about what I mean by slice. I started with a random slice, and I said that it converges to a limiting space, which is a sphere. Bon. What does it mean? It means that with this, in this theorem, I really think about the slice as being a rooted and pointed map in which I haven't, of course, cut open the geodesic between the root and the distinguished vertex. Okay? But there is actually a version of this theorem in which you do consider the slice as maybe in the more intuitive way, meaning that you actually cut Mn along this leftmost geodesic, and so what you obtain is maybe something like this. Okay, so let's call it Mn open, and it's actually also true that this Mn open with the graph distance rescaled by n to the 1/4 times this little constant sigma. This is not epsilon, right? This is sigma. Converges jointly with the above convergence to say S open, D open, okay, which, let's say, a continuum slice, which is obtained exactly in the same way by cutting open the Brownian map along the distinguished geodesic between two marked points. Okay, so maybe I should be more precise about this. So the convergence result that I gave earlier, the one that is stated over there, tells you that this random metric space is going to converge to this limiting space SD. Somehow there is an improved version of this theorem in which you actually keep track of the position of the root and the distinguished vertex. So they actually converge to two marked points in this random space, which you should think of as being points chosen uniformly at random. And then, since the limiting space is a geodesic space, you can draw a geodesic between these 2 points. And it turns out to be almost surely unique, in fact, this geodesic. Okay? And then it makes sense, again, to cut open this geodesic, although it requires a little bit of formalities, let's say. And the opening of this space is going to give the opened Brownian slice that I described earlier. Okay. And so actually this kind of convergence is instrumental in Le Gal's approach to this theorem. So I should also cite here the work of Le Gal. So you might wonder why it's it's important to have these separate results, but it turns out that these slices, as we saw last time with the description of maps with a boundary, they are in fact building blocks for more complicated random objects. And I should state here a result which tells you what you obtain when you consider this time not slices or pointing on routed maps, but maps with a boundary. Okay, so maybe a consequence or theorems, which is due to Bettinelli and myself, tells you that. So let's say mn be a sequence of numbers which is like let's say L times square root n for some L greater than or equal to 0. Okay, as n goes to infinity. And let Mn be a map with distribution, let's say WQ, but this time conditioned on the set of maps with perimeter, I should say 2Mn, and with n edges. Okay, so I'm not sure if I made myself clear. So I restrict the measure WQ to maps in which the root face has degree 2Mn, where Mn is the sequence of numbers of the square root of n, and also which have n edges. Okay? So maybe I should keep the notation Mn here. Then, again, we have a similar kind of limiting result. So the number of vertices of Mn with the graph distance, rescaled in the same way as before, converges as n goes to infinity and in distribution in the Gromov-Hausdorff sense to a limit, which I'm going to denote by dl, which is called the Brownian disk with volume 1 and perimeter L. Okay. So we get a one-parameter family of limiting spaces, and these limiting spaces do have, in fact, the topology of disks, but they have a boundary which is also fractal. Which a way to understand that is that the distances are typically of order n to the 1/4, but the boundary length, as I mentioned here, is typically of order the square of that. Okay, so if you like, the boundary is a curve of dimension 2 in the map, and the outer dimension of the map, let's say seen from a point inside, is still equal to 4. Yes.
So for all these results, you have the version with the measured,
Yeah.
right? So,
Yeah. Absolutely.
So to make the relation with the.
Yeah. Exactly. So I said that. Yeah. Okay. Okay. That's a good point. So two comments about this. So first of all, I said that these points here are like uniformly chosen points. In order to choose points at random, you should have a measure on the space, and it's actually possible to do. So there is a version of this where you add, let's say, the uniform measure μn on vertices, and it will converge in some, in some extended way, let's say the Gromov-Hausdorff-Prokhorov distance, to a measured metric space. And I think the point that Wendelin wants to make is also the fact that in these questions that were discussed by Nina and Jason about embeddings of maps, this measure mu should correspond to the gamma LQG for gamma equals to square root of 8/3. Okay, that's. I mean, in Jason and Scott's construction of the Brownian map out of the GFF that I don't have time to describe here. The gamma LQG measure for this particular value of gamma actually plays the role of mu. Okay, but maybe the more general conjecture that you can have is that if you conformally embed in one of the ways that Nina discussed these objects, say in the disk, then in the limit this should correspond to these gamma LQG measures. Are there questions about that? Okay, so just very briefly, so because my title talked about slicing, so we have seen slices, but so far maybe they've played more of a combinatorial role than a concrete role. But what I want to emphasize is that this result with Bettinelli is actually obtained by really a continuum analog of the slice decomposition of Boutier and Guiter. So let me briefly, not even sketch, but give an idea of what's going on here. So Mn of Mn, so via a slice decomposition. So if you remember, maps with the boundaries, they can be described in terms of the labeled, the distances to a distinguished point inside the map. So let's say that we mark a point uniformly at random. So you get the distances to the distinguished point, and that gives you a bridge, a discrete bridge. Let's say something like this, with increments plus or minus 1. So this is something that I described last time. Okay, so this bridge actually stops at 2Mn. Again, so these are the distances to V star. And then once you have it, you should assign every descending step a slice. Okay, so you have maybe an object like that for every descending step. Okay, that maybe something like that. Okay. And what I was saying was that in order to get back the map with boundary, what you should do is that you should glue horizontally all the green parts to the red parts that are facing them. Okay. Well, another way to say that is that inside this map with a boundary, you have the slices that sort of are drawn in this way. Okay. So again, I'm not going to be more precise, but you have a kind of decomposition of this mirror-like object into shards. And actually, you can pass to the limit on this picture just by using this theorem. Okay, so this has a natural continuum analog which is given by a trajectory of this time a Brownian bridge. Okay, so actually with a certain scaling factor. On top of which you put a Poisson process of slices. Okay, so of course there will be infinitely many slices in the end, but otherwise this is actually the exact same picture. Okay, so you can actually construct the Brownian disk dl from this object. Okay. I'm not going to say much more, but it's just to tell you that it is possible to use this result as an input to obtain results about other types of surfaces. Okay, so in the remaining, I guess, 3 minutes, I want to comment on the fact that this is not at all all that you can get from this model. And even though the result that I stated here has this kind of universal quality to it, okay, as soon as you have this critical weight sequence with finite variance, you will always get the Brownian map in the limit. Things are also very interesting when it so happens that you don't have a finite variance. And this is what I want to comment on now. So let's see. Okay. So now assume that Q is still critical, but that it has fat tail, so that it is in the domain. Not actually mu q. Mu q is in the domain of attraction of a stable random variable with exponent alpha, and the relevant values of the parameter alpha here are between 1 and 2. Okay, so this actually can be achieved by considering a sequence of the form c times b to the k times q naught of k, where q naught of k is equivalent to some constant, let's say 1, divided by k to the, I guess this should be alpha plus 1/2. Okay, so this is actually something that actually occurs in applications. So my point here is that if you fix a sequence like this, having this state behavior, then there is actually a unique value of C and B such that this weight sequence QK defined in this way satisfies this property. Okay? So there is, I mean, there are lots, of course, of sequence Q that satisfy this property, but somehow you have to choose them in a very, very careful way. And so the reason for that is that somehow you should both have criticality, but also the generating function of size should also correspond exactly to the radius of convergence of the series GQ, and that gives you, let's say, another constraint. Okay. Then we have a theorem, so which is due to Le Gall and myself, and actually maybe in this generality it has also been improved by Marzouk. That tells that, so if Mn is as before, and assuming Q is as above, meaning critical and with mu q in the domain of attraction of a stable random variable, then from every sequence of integers, one can extract a subsequence along which we have the convergence, the following convergence. So V of Mn and d Mn, this time divided by n to the 1/2 alpha, this converges in distribution to an object that I want to call S alpha G alpha, which is called the alpha stable map. Okay. So two comments are in force here. The first one is that the limits will have a very different behavior than the Brownian map. You can see from the scaling that the dimension is typically different. It's 2 alpha and not 4 anymore. Okay, and it will be 4 when alpha is equal to 2. If you want the limiting case alpha equals to 2 corresponds to the Gaussian case, in which case we are back to the previous setting. Another comment is that we have this extra subsequent things. We don't actually know that the limits are unique here. Okay, this is something that has not been done. And okay, maybe just one comment, because I won't be commenting a lot more on this. So I will come back a little bit to this situation in the next lecture, but maybe not from the point of view of these table maps. So what I want to say is, first of all, so where does this come from? This comes from the fact that vertex degrees in Tn can be and will be as large as n to the 1 over alpha in this situation. And if you remember the rules for the labels, if you have a vertex with very large degree, then the label differences is just going to be a kind of random walk with this length. So this means that the labels will be of order n to the 1 over 2 alpha, the square root of this. Okay. Again, because of the central limit theorem. So that explains the scaling here. And that also explains that this corresponds to faces of very large degrees, which means that the stable maps are a kind of random map, let's say RPM analog, of CLEs. Okay, so there are objects which are, if you want, Sierpinski-like fractals, okay, in which you have very, very large faces. And there is actually a very interesting phase transition happening exactly as in CLE about whether these faces intersect or not. So this is the first comment. And the last comment is that these maps, this situation arises naturally in the critical, rigid ON loop model that I described last time, with alpha here being a 3/2 plus or minus 1 over pi arc cosine of n over 2. So what I mean is that if you take the rigid ON loop model that I described last time and fix n and tune the parameters in a critical way, then the gasket that you will obtain will fall exactly in this kind of in this class of maps. Okay, and this is due to Boromouté-Guiter. And I should also mention that it was completed in the work of Chen and also Bud very recently. Okay, I'm done for today. Sorry for running over time.
So you also have convergence for the measures there, and
yeah.
So the volume of the measure will be what type of?
This is a kind of unit volume object. If you take the uniform measure on the set of vertices, then you will get a probability measure here, and this
dimension of.
Sorry.
And dimension of that thing will.
Yeah, I'm not sure. I guess you should know it better than me. But yeah, I mean you
have
get
it, I mean,
yeah.
Yeah, we can answer it. It's a good question.
Okay, just a small comment about the theorem, the convergence of two entities. You also have a version of the theorem where you don't condition the number of vertices, which is very natural.
Yeah, that's right. I mean, I guess here the point that I wanted to make was that I wanted to stress the scaling between the total volume and the perimeter length and the distances. I think in this way, I mean, okay, so what Jean-François is saying is that if I just take M, go to infinity, and consider a map with a boundary size M, but without a fixed volume, then we also have a scaling limit result. In this case, you have to rescale by the square root of M, sorry, and the limit is again a disk with a perimeter L, but with a free volume, with a random volume, and it's also, of course, a very natural object. It's it has a lot of nice properties. Actually, next time I'm going to be focusing more on this kind of objects when I will discuss peeling. But again, my point here was that in this formulation, you see, I think you see very well the scaling relations between the total volume, which is equal to n, the perimeter length, and the typical distances. But yeah, absolutely. I mean, this is a kind of conditioned version of that. Yes, Scott.
So what is missing in order to show that this is a unique object in the limit?
Well, it's always the same the same story. I mean, these bijective proofs, they allow you to deal with distances to a particular marked point, and you have to show that the other distances can be deduced from these very particular trajectories. And yeah, and I'm not saying it's for instance very much more difficult than this theorem, but at least you have to have a slightly different intuition on this. It's not the case.
Try to just follow the recipe that works for the Brownian map. At which step does it break?
It's a long recipe, so yeah, I'm not sure about that.
Okay, so then we can thank Gregory.